Well, here we are the next morning with a bit of a fuzzy head from all the beer. Well, I only had about 3 bleeding cans, but anyway. So sorry it got cut off a bit abruptly. Still can't talk freaking straight. Sorry it got cut off a bit abruptly last time. The memory went on the old camera. We've got basically 3 capacitors and 3 resistors. And hopefully this will sort of clear up or make more clear what I was on about corner frequencies, high pass filters and all that malarkey. Forget all these op amps here, they're just there so I don't lose the buggers and stand on them. What I was trying to get at was that each RC stage in our amplifier just on their own will attenuate or make smaller the signal that we put in. Obviously, like this is basically representing each RC filter in a 3-stage amplifier. So if we come over here, this is what we've got. We've got 100 nanofarad cap with a 1K5 resistor. Right, I ought to put that in there, haven't I? 1K5. They're all 1K5s. These are all 100 ends. Okie dokie. We're putting, this is all sort of ish. I can't get this bang on without lots of mucking about. So we've got about 1 volt RMS going in. Okie dokie. And then we'll go over and have a look at the scope. So we're not really bothered about absolute values here, but I'm just trying to represent it visually, which is easy to get your head around. So that's the waveform there, that's what we've got coming out after this first RC filter here. See, this is at this point. Right, now then, if I move my scope probe, put it on the second RC filter, it's gone down. Now if we did the calculations, that should be half as big again as what we put in. It doesn't quite work like that because we're talking in decibels. So there's 1 volt going in here, we're not getting half a volt here. We're talking in decibels, which is some sort of weird logarithmic craziness. But hopefully you will see the point. And then if we move our probe again, it's gone down even smaller. So I'll move the probe back the other way and you'll see the difference. And if I put it, oh dear, we've got a bit of a right, and that's our signal going in. Obviously you can't see that because the scope isn't set up properly. See? Big, smaller, 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 smaller. So I hope that sort of makes clear the situation that we've got in an amplifier and what I was going on about, well, it was yesterday in the last video. So these are the measurements that I just took. We've got about 1 volt going in, 1.039. Well, it's now 0.36. And if I move that onto here, that is about half a volt, so we weren't far off, was we? So I was probably wrong in what I was saying. I don't know all this stuff by heart, I'm a bit sort of vague myself. And then we've got at the last stage, well no sorry, that's our next stage, 0.22, and on our last one 0.15. If we did the sum, which I think from the top of my head is the voltage, whatever a voltage is, V times 20 log, or it might be 10 log times whatever. So in an amplifier, what you're trying to do we don't want that signal to be lost too much. In this case we've got a 1 kilohertz signal. I just chose that because it was just an easy frequency to choose, making the choice of the capacitors and resistors easy-ish. To get a proper 1 dB attenuation, that should be more like 1K6. So our values aren't exactly right and our voltages aren't exactly right, but I just wanted to try and illustrate the point. So in an amplifier we don't want, obviously we're going to stick a signal in, and although it is amplified, we don't want our frequency to drop too much, do we? So for instance, where are we? I'm all over the friggin' shop here. So for instance, say if that's going into our first valve there, let me just sort of try and draw that. I hope I'm making this clear. It's quite hard to it's quite hard to describe. So say this is our first RC filter going into our first valve. There. You sort of have to guess the rest, okay? We've got a resistor here, anode resistor. There we go, that's going to ground. So what we don't want, we don't want to choose out the wrong capacitor values, so that if we stick in, let's just say 1K, 1000 Hertz, just for example, we don't want to then choose our next RC filter. We're using an RC filter because this is blocking DC. We don't want DC on the next valve's grid, do we? So we want to choose those capacitors and resistors such that there is as little attenuation of the frequency that we're bothered about as possible. Because this is a high-pass filter does this sort of thing. If this is our sort of graph, and we've got increasing frequency going up here, so 0 Hertz here, whatever, 1000 Hertz here, and this is voltage, this is our amplitude, you'll get something like that. So say up to about, let's just say 20 Hertz for example, our frequency will be going down. We want to choose our capacitors and resistors such that it goes all the way, straight all the way through. We don't want it to go through like that, say, do we? Because it's an amplifier. We're trying to amplify all frequencies, if we can, at the same amplitude, at the same voltage. So how you find that is using this formula here. It looks complicated, but it is quite simple once you've used it a few times. 1 divided by 2 times pi times your resistor times your capacitor, or I've written it differently here, 1 divided by 6.28, because pi is 3.14, times by a frequency, times by a capacitor or resistor. They're all F, R and C are interchangeable. So this is how I found, I have my calculator ain't working, so I had to use that online calculator that I showed in the last video. So 1 divided by 6.28 times by 1000 times by 0.000001, because we use the capacitance must be in farads. A farad is like, you know, a basic measurement of capacitance. 1 microfarad, well sorry, 100 microfarads would be 0.000100. This is 100 nanofarads, so it's down here with loads of zeros in front of it, and that gives us 1.59 kiloohms. And I didn't have any 1.59, so I just used 1K5 or 1.5k. Let me just knock that down. So I hope that makes sense. So that's what I was going on about yesterday, corner frequencies and all that. Why they're called corner frequencies, I don't know. Maybe they're disreputable when they were younger and hung around on the street corners getting into trouble with the police. I do not know. I'm being facetious there obviously, but yeah, corner frequencies. And other things come into it like poles and all sorts of crazy things. And imaginary numbers even, when you're trying to get into some of this. I try and stay clear away from the imaginary numbers, which looks like a sort of a weird W or an arse. I try and stay away from that sort of shit because life's sort of complicated as it is without getting into imaginary weird universes and things. So yeah, hope that makes sense. So just did that as a way of demonstration. Next we'll get the capacitor. The capacitor? There we go again, the brain's going again, look. We'll get the amplifier on the bench in a minute and we'll do some testing. So this is how our amplifier will look. Unfortunately some idiot drilled like a load of bleeding holes, which are now no longer going to be used. So what I've done there, this is just a bit of scrap metal. Obviously needs painting and just shaping a little bit better there. I'll just use some of these like blanks to blank off these 3 holes here, and then obviously I'm going to have to try and clear up some of these holes as well, which don't look very good unfortunately. So that's the plan anyway. So I'll flip it on its head and then we'll do some testing. Oh yeah, what we've got our, oh what the bleeding hell are they? Yeah look, I'll just show you the box, save me saying it. There you are, that's what they are. Them things. Sorry it's a bit late in the day. So there's our output valves. Look quite snazzy, don't they? We're going to have a 12BH7 as the phase splitter, and we're going to have a 6CG7 as our input valve. We'll be connecting both triodes in parallel to get more gain, and also it will fill that hole. Otherwise I would have to use either a single triode or a pentode. So right, I'll flip it on its head and we'll do some testing. Right, so can we see that alright? Can you see that alright? Can we do it with that? Yeah, we can't. It's, are you going to be good? Are you oh, there we go. Right, are you focused? Are you paying attention? Good, good, good. So here we got a rough schematic of the amplifier. A lot simpler than the other AB2 jobby. There's our output valves. This is all that resistory network thingy that I was showing you yesterday to balance each side of the push-pull output stage up. Those are those 10k resistors, can you remember me telling you about? Obviously I haven't put the 1 megs in there. These are our grid leaks, 100k. There's our capacitors that we worked out, the 220 nanofarads. If I used the 47 nanofarads that I had in there, it would have attenuated the higher frequencies. I don't know exactly what frequency, but yeah, we wouldn't have had very good bass. 47k anode resistors on this phase splitter here. That is, well, instead of having a tail resistor, because this is a long tail pair, we've got a constant current sink, which consists of a BC5498, oh no, sorry, BC549 and an MJE340. So we've got a Zener diode there that fixes the base of the BC549, and then we've got a couple of drop-in resistors. This is a 33k and this is a 3k3, and that's just to supply the Zener with enough current to work basically, and to also sort of fix these by base voltages. I'm rabbiting on again and forgetting what things are called, sorry. Blah blah blah. So yeah, that basically, a constant current sink is better than a resistor. At AC current, it has a very high impedance. If we used a tail resistor, say 30k or even less, that isn't as high AC impedance as this constant current sink, which has, I haven't worked it out, but it will probably have an AC impedance of about 1 meg plus, so we get a better balance. Sometimes you see on phase splitters that just have a resistor as a tail resistor as the constant current source sink. You'll see that they have either a pot here to balance the AC signal coming out, or the blinking memory went there again. So we've got a what were we looking at? I can't remember what the figure we were doing. Anyway, that's our schematic. I'll go, if you want me to, into more detail about how I got the various values. We've got no input valve in at the moment. All we've got is the phase splitter. This is just what I propose to put in. Whether it'll work or not, I don't know. So there we go. Some of this is a temporary. This here, this pot here, that is setting our bias at minus 26.26 volts. Blah, blah, blah. I've tested all the other things, so let's have a look at the DC voltages. Some of these are off, so I've got to change some values. We've got 400 and, hopefully you can see that. Can you see that? 430 volts HT. That will drop when we get the other valves in. Our second HT here, at this capacitor here, which is a decoupling capacitor for the phase splitter, is 377. I designed it for 350, but there's a few things wrong. This resistor here for the constant current sink is wrong, wants to be smaller, because our cathode voltage on the phase splitter is 8.5 volts when it should be more like 7 volts. So we've not got enough current going in there, I don't think. What else? Yeah, the drop-in resistor that we've got on our bias pot setting voltage thingy is an 18k. That wants reducing to maybe 15k so that we can get a bit more bias voltage on the output valves. Sorry, my voice has gone. Because the cathodes are at 53 what are they? 53 watt? 53 milliamps. 53 milliamps and 47 milliamps. A little bit high maybe. I'd like them a bit lower. Our screen grid voltage is at 301. Anode on our phase splitter 198, 184, so about 200 volts ish. Yeah, that one's coming down a little bit, but it's still within spec. And so let's have a look at an output. Whoops. That's looking good, isn't it? That's what we've got coming out, and this is with 1 volt going into the phase splitter. And let's have a look at the total harmonic distortion. Ooh, 0.8. Right, let's have a look at lower frequency. Frequency 20 hertz. Ew, that's not looking good, is it? Look, look at that, 35. Where are we? Let's try and get that. That is looking friggin' horrendous. It wasn't like this the other day. It was a lot better than that, but that was the sort of thing I was getting with the 6146s. Let's just knock that up a bit. Frequency 100 hertz. So that's better there, look. 100 hertz. Distortion 7%. Still not good. I think what it is them sodding output transformers. I think they've got really crap bottom end response. I might even change them if I can afford a pair. So the voice is going. But we're good at 1 kilohertz. Let's just go up the other way. Frequency 20 kilohertz. We're still pretty flat. Where are we? 4.83, frequency 1. Right, so we've got a bit, it's peaking a bit. So come on, you fricker. Right, that's 20 kilohertz. No, it isn't, it's 1 kilohertz, you peanut. Frequency 20 kilohertz. But it's still within like 1 dB, I think. Try 50. Still good luck. We haven't fallen much at all. So, frequency 1 kilohertz. So, our frequency response is good. However, the low frequency response is and the distortion is really shit. I'm sure it's those output transformers. It's got to be. I've changed the valve, so let's see what we can get out of it. Amplitude 2 volts. Oh, that's knocked it up a bit. 9.5 volts RMS. Still looking good. 1.3% THD. Go to 2.5 volts. Amplitude 2.5 volts. 12 volts RMS. Still looking good. Amplitude 3 volts. Now we're starting to clip a bit now, look. See, just in the top and bottom there, 14.9. Amplitude 2 volts. So 15 volts RMS. Get this sorted. So 15 volts, I think it's about 20 watts, I think, which these 6BG6GAs, that's what they're rated for. I think 18 watts, 20 watts. I've heard you can get more out of them, but I'm not bothered about that. That's fine by me. Obviously we're going to lose some of that if we apply negative feedback, but 15 watts is 15-20 watts is more than enough. Right, my voice is going. I need some beer. Go and have a relax. It's been a long old day. My back's giving me jip and what have you. Hope that all made sense and was mildly entertaining. Thank you very much for watching. Take care of yourselves. Ta-ra for now.